Hello again, this is Mark Summers from Summers Technical Services. We're going to follow up our assignment from class earlier on the spring design and do a finite element analysis using Solidworks simulation. Normally you wouldn't do simulation to figure out what your spring stresses and displacements are because we can calculate those from the manufacturing data at Lee Spring. But this will give us a chance to learn how to use SolidWorks in simulation, and we can verify to make sure our numbers that we calculated match up reasonably well with simulation. So as a reminder, here's the, drag it over here, here's the fixture that we're using as our design input. And it's got the multiple springs on there, these Lee Spring hefty die springs that we did the analysis on. And we're going to do, the simulation is going to be just one of them, even though you have 6 or 7 or 8 springs on the total design. We'll split that 1,000-pound load up into evenly distributed among the number of springs you have in your design. So let's minimize this thing here. And here's the model. I've give you your models for the different springs you're using. This was different than what you're using, but the idea will be the same. So the first thing you'll want to do is come up with material properties using either the Lee Spring data sheet, the material sheet that we went over in class, or in some cases I'm having you go use information at ASTM A401. And those references were written on the board last time. So use those. This is the material properties, if I can find my little screenshot here. So these are you'll have to make your own custom material because there's not one called chromium silicon alloy steel. So you have to make a custom one like we showed you how to do in class. And the values you're going to enter are elastic modulus, Poisson ratio, shear modulus, mass density, tensile strength, and yield strength. Make sure you've got the right units in there, and you can toggle these between English and metric units. Keeps track of the units for you, but you got to make sure you type in the right number based on the units that are showing in the material sheet. So let me drag that out of the way. So here's the spring. We're going to go through the steps to do your simulation. First thing you have to do is make sure you've got your simulation add-in loaded. If not, go to Tools, Add-ins, and turn on the SolidWorks simulation add-in. So you'll have this tab here. And pretty much just answer questions left to right and run the simulation. So first thing I'm going to do is click on New Study. And I can give it a name. I got lots of different options down here. This is going to be a static simulation, so I'll just take the default settings and say OK. Next thing I'll do is, next button is Apply Material. I've already assigned the material in the custom material in SolidWorks part model. So now all I need to do now is say Apply Material and hit the Apply Close button. And now that material is assigned in SolidWorks simulation. Next button is going to be the fixtures. I want to fix the bottom one to be a fixed constraint because the bottom of the spring is fixed to the bottom plate, and it's going to be guided in the X and Z directions in my model here by that standoff on the base, so it's not going to be able to move in any of the 3 directions. So I'm going to do fixed geometry and spin this around to the bottom and just grab this bottom flat on the spring. And I might go over here to these symbol settings, make it a little bit bigger so I can see it. You can see it better. And now that bottom face is fixed, and you can see the little icon there. It's got the arrows pointing in all 3 directions, so I know that thing is constrained in all 3 directions from translating. On the top side, it's going to be a little bit different in the fact that we can't constrain it from moving up and down because that's the direction the spring is going to be deflecting. But I want it to be, I want it to stay flat, so it can't, so it's free to move in the, in this case, X and Z direction. So I'm going to do a little bit different constraint. So I want to say, I'm going to use fixed geometry again, but I'm going to use an advanced feature to make it so I can release the side to side and front to back constraint. So I'm going to click that face like I did a minute ago, and I'm going to come down and define a direction to define which direction I want to constrain. And so when I come down here to the Advanced tab, I want to select on the face to define the direction. This box right here, if I hover over it, it tells me select the plane for direction. Make that box active. I'm going to select the top plane. That'll define a direction up and down. And the constraints I want to have perpendicular to that face. This one I want to be free because I want it to be able to move up and down. These other two I want to set to 0 because I don't want it to move side to side or front to back. And so I'll say OK on that one. I want to go ahead and add this symbol scale so I can see it. You can see it. And you can see these arrows up here, they're only arrows in 2 directions because I'm constraining it from moving in those 2 directions, but it's free to go up and down. Now I need to put my load on here. And I've got, let's see how many springs I have on mine. So I've got a spreadsheet here somewhere. And I've got, looks like I got 7 springs. So I'm going to use that to divide my 1,000-pound load up. So I'm going to come over and say the force on this top face, use that same face there, it's chosen the right direction. Make sure you get your units set correctly. And I need this to be 1,000 divided by 7. And say OK. So now I've got my constraints, I've got my material, I've got my load on there, and now I need to do the mesh. And I'm going to create mesh, and I'm going to use an advanced option because due to the nature of this helical spring, I think I'm going to get better results if I, not advanced, but mesh parameters. I'm going to use this curvature based mesh. And then I'm going to slide this slider. Depending on how fast your computer is, you may or may not be able to crank it up all the way to fine. I got a pretty speedy computer, so I want to crank it over there. Curvature-based mesh. And then we'll see what this mesh looks like. Take just a few seconds. And then once we do this, we're going to run it. So before I run it, I suggest saving your file so that in case something crashes out, you won't have to start over completely. Yeah, looks like it's through the mesh, and that looks like a plenty fine mesh there. So let's go with that. I want to say file save. And the last button you push is just say run this study. You go full screen here, run this study. And since this is going to have relatively large deflections, it may give you a pop-up window to suggest that you use the large displacement options. It uses an iterative process to get the large displacements taken care of. And sure enough, it's warning me, hey, successive displacements were calculated in the model. Blah, 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 and it basically just says, hey, we suggest you use this large displacement. It's going to take a lot longer to run, but I'm going to get a better answer, so I'm going to choose yes. And I like to hit this more button here, kind of get an idea what's going on in the background here. So if I click on this convergence plot, it's kind of interesting. I don't quite understand every aspect of this, but what it does is it iteratively solves and gradually adds more and more of the load, and it recomputes the stiffness matrix after some amount of displacements occurs. So right now it's on step number 1. It's in this large displacement mode, and you can see these convergence plots, P1, P2, P3, P1. These are polynomial, so first order polynomial, second order polynomial, and it's tracking to see how well the finite elements that it's created are converging for the different orders of finite elements is created. And when it hits the threshold line, it goes back and starts over and does this iterative process. So you can see now it's still on load step number 1. And it will go through and start over again. You can watch the convergence plots for the different polynomial degree orders. And I think what I'll do is I'll pause the video now. It usually takes about 10 minutes to run this thing. So we'll pause it for the moment, and then I'll come back and see what the results are. Okay, it looks like we're back here. Got the model finish running, and it's got some default results here we'll go through. So it gives us this von Mises stress. It's useful if we're doing failure theory for ductile materials, but this isn't a ductile material, so we need to get the stresses we're interested in. We're interested in the shear stresses because that's what we calculated with our hand calculations, and that's the failure mode of these springs, is they generally fail in shear failure. And so we've got our calculated there's my calculated deflection at 1,000 pounds, so I'll highlight that one. I want to check that number, and we want to check our operating stress. That's what our calculations told us, and then we'll check and see what the model tells us. So first thing I want to do is check on the vertical displacement. So I want to right click on results and say define displacement plot. And the y direction over here on the triad is up and down, so I want to ask for the y displacement, and my answer was in inches, so I'm going to ask for it in inches, and I'll say OK. And it's in this deform result mode. You can turn that on and off, and you can play around with it and animate it if you want to kind of get a feel for what's happening. So it looks like it's got a little side to side, may have some buckling issues with it. And so I'm going to look at the displacement in the x and z direction, see how far out of plane that's going, and help me decide if maybe I need to look at the buckling of the spring. So anyway, in the y direction, let me stop this animation. In the y direction, it's telling me the maximum displacement is blue up here at the top is 1.5 inches, and that matches fairly well with my calculated displacement. So I'm going to type in 1.525, and so those compare relatively well, so I'm going to feel good about that. Now I'm going to go to get my shear stress and see how they match up. So I'm going to right click over here. First thing I want to do is check that other displacement. So I'm going to define a displacement plot in either the x or the z direction. Again in inches. And I'm going to see that it is largest here. Whoop, that's not what I wanted. No, y. I want x. Here we go. So side to side, it's staying straight in the middle, but in the middle of the spring here, it's moved over. It's 0.17 inches. That's almost 3/16 of an inch. So that's somewhat worrying. My standoffs that guide it are only guided for the first half inch or so. So here's the standoffs themselves are an inch tall. So this might be an issue I'm going to address later. I believe your springs are much shorter than this one, so I don't believe you've got buckling problems. But on mine, potentially have a buckling problem. So let's go look at the shear stress. I'm going to right click on results again and say define stress plot. And I've got three choices, as we've learned when we did our Moore circle combined stress assignments. I've got three shear values. There's 6 of them total, but 2 of them, the pairs of them have the same values, opposite signs. So I want to ask for shear in the XY direction. And again, since I've got my answer in PSI, I want to ask for it in PSI. And turn off this deform result. So here's what I'm getting. And what I want to do is compare it to my calculated stress, 101,062. So the way I like to visualize this is go up here to Plot Tools and go ISO clipping, and I can clip it such that I'm only seeing stresses above whatever value I happen to want. So if I type in 101.062, I can see the only place that's higher than what I calculated are the very tips of these springs over here. So I feel pretty good that the stress in the simulation is relatively close to the maximum stress. If I bump this up to like 105,000 maybe, it's going to be even smaller slivers of it. 110,000. They're virtually gone now. So I can feel pretty confident that my answer is within about 10%, say, of the calculated value. So I feel pretty good about that. So when you turn your assignment, just do this ISO clipping, get a number there that you're confident is capturing, 90+ % of the high stress levels, and just so you show me that your numbers match, you can be confident your numbers match. So do 4 screenshots, 3 of the 3 shear stresses, and 1 of the Y displacement, so I can see that you check that. So let's go check the other shear stresses. So I got shear XY plane, or X face in a Y direction. Define another stress plot. And choose the next one, which is shear stress on the X face in the Z direction. Again in PSI. And do the same kind of a thing. Go to Plot Tools, ISO clipping, and you're going to use your value of your maximum operating shear stress you calculated, and then see how it compares with. So here it's obvious that everything is below that value. So, and there's some kind of, it'll have some kind of small rim in it. This the only piece that's higher than that. So we can ignore that as some kind of a mathematical singularity type down here, where it's got a funky element right there at the end. So I feel pretty good about that. And then we'll do the last one. Right click, define stress plot, and then the last one I guess is going to be what? Shear on the Y face in the Z direction. And all these values should be the same theoretically, but the simulations will be slightly different. But let's see what this one said. Plot Tools, ISO clipping. Just look at all the stresses that are above what I calculated, 101.062. So it's the same kind of picture. It's just very sliver piece left here that's above that stress. So again, within 5 or 10%, I think I've got the right values. So with that, I'll let you finish up the assignment. Submit your model, just the SLD PRT model, so that I can see that you've got your material properties defined properly, and then send me those 4 screenshots, and that'll complete part C of assignment 18. So until see you next time, enjoy the rest of your day.